Yeah, welcome to the lecture today. I would like to recall some elementary things. So first of all, let us recall some elementary properties. Some elementary properties of the Fourier transform. As follows. First of all, I would like to recall the definition of the so-called Schwarz space. So let S of Rd be the Schwarz space consisting of smooth functions phi and c infinity on Rd, such that we have the following criterion here: 1 plus absolute value of x to the power of n times the derivative of order alpha of phi as a function of x, such that this expression is bounded and this holds for any n in n, and for all alpha, which is a multi-index in n0 to the power of d. Yeah, this is the Schwarz space, as you know. And then I define the Fourier transform. So let this be S, and so let this be the Schwarz space. It's named after Laurent Schwarz. And define the Fourier transform. And define the Fourier transform on S. Which is then a map F on S, and it also goes to S of Rd by the following definition. We say that f acts on a function phi, and it is then a function of a variable k. This is then defined as 2 pi to the power of minus d over 2, and d is the dimension of our space. Integral over Rd exponential minus I k times x, phi of x dx. And we also know by Plancherel's theorem, so by Plancherel, we also know that the norm of f phi is equal to the norm of phi for all phi in the Schwarz space, S of Rd. And furthermore, we can say that for any psi in the Schwarz space, there is phi in S, such that we have that f phi is equal to psi, and clearly this defines then an inverse map. So this defines the map f to the power of minus 1, the inverse, by phi is equal to f inverse applied to psi, And this is then 2 pi to the power of minus d over 2, integral over rd exponential I k times x psi of k dk. Yeah, here we have no minus sign, and here we have the minus sign. Yeah, we are interested in a Fourier transform on L2, and it is possible to get it from this definition. Now we can say that as the Schwarz space S of Rd is a dense subset of L2, so as this here is dense, we can apply the BLT theorem. Yeah, so the BLT theorem, which stands for bounded linear transformation. And this theorem then yields a unique extension, to an operator on L2, to an operator F that acts on L2. And here we have the following definition. I will only give you the result because this is standard, I think. So here we have that Fu of k is the L2 limit when we send r to infinity of the following 2 pi to the power of minus d over 2. And now we have the integral over a ball of radius r exponential minus I k times x u of x dx. And this holds true for all u in L2. Yeah, we had also seen that the Fourier transform allows us to diagonalize the Laplace operator. So if we have a self-adjoint version of this operator, we obtain a diagonalization via the Fourier transform. So we can say the Fourier transform allows for diagonalization of the free Laplace operator. So we had H0, which was minus the Laplace, first defined on CC infinity, and then we take the closure to obtain a self-adjoint operator in the Hilbert space. And precisely, yeah, this means that the Fourier transform applied to H0 applied to f to the power of minus 1 is exactly multiplication with the variable, or the absolute value of the variable, to the power of 2, where this operator here is the maximal multiplication operator, is the maximal multiplication operator in L2. In L2 of Rd, corresponding to the function q of k is equal to the absolute value of k to the power of 2. Yeah, and we also know that if we take a continuous and bounded function, so for all continuous and bounded functions f, for all continuous and bounded functions f from R to C, we have that the Fourier transform applied to f applied to h0, so this is the function of this operator, applied to f to the power of -1 is then multiplication with f of this function that produces the square of the absolute value. Okay. And then we have another well-known result, which I would like to recall. It's the Riemann-Lebesgue lemma that we will need. So let's recall this. I have here theorem 4.14. Theorem 4.14, which is the Riemann-Lebesgue lemma. And it says the Fourier transform maps L1, maps the space L1 of Rd continuously to the space C0 on Rd, which is equipped with the usual supremum norm, where this space here consists of continuous functions. So C0 of Rd is the space of continuous functions U on Rd, with the property that U of x converges to 0 whenever x becomes large. And of course, the supremum norm, so the norm of U in this space is simply the supremum taken for x and Rd of the absolute value of U of x. Yeah, and it's also important to remark that this map is not onto, so remark 4.15. Note that the Fourier transform as a map from L1 to C0 is not surjective. This is important to keep in mind. Okay, now let's have a look at what we actually want to do. Our intention is to prove the following results. So let A and B be self-adjoint operators in the Hilbert space H. Here we take two self-adjoint operators and we assume that they have the same domain. Then we want to show the following. Then we show that if the difference A minus B is a trace class operator, so if A minus B is in the trace class, then we claim the wave operators omega plus minus AB exist and are complete. And this is the so-called Kato-Rosenblum theorem. And number 2, we show that we have a similar result when we use the resolvents here. So if the difference of the resolvent operators is trace class, and then we claim similarly the wave operators omega plus minus of AB exist and they are complete. Exist and are complete. And this is the so-called Kuroda-Berman theorem. Yeah, recall here, so this is a short reminder that we defined omega plus minus, these wave operators, as the strong limits for t going to plus or minus infinity of exponential ita exponential minus itb, and here we have the projection onto the absolutely continuous subspace of H with respect to the operator B. And we said that these operators are complete. So we said omega plus minus are complete if and only if we had that the range of omega plus is equal to the range of omega minus. We called these spaces H in and H out. You recall this? And both are equal to HAC with respect to the operator A. And we also know from one theorem that we already had that omega plus minus of AB and these operators are complete if and only if omega plus minus of BA exist. Yeah, this is what we already had shown. Okay, let's note this here. First of all, both results, the Kato-Rosenblum theorem and the Kuroda-Berman theorem, will follow from what we call Pearson's theorem. We will give a proof of this important theorem in detail. And regarding proposition 3.9, so regarding, this is what I recalled, regarding proposition 3.9, we know that it suffices to show that both operators omega plus minus AB, or both pairs of operators omega plus minus AB and omega plus minus BA exist. Yeah, but nevertheless, it is not straightforward to apply the methods that we had derived so far, because, for example, if you think back to the Cook-Huck theorem, we had the situation that one operator is simple and the other one is more complicated. Yeah, for example, we had A, this Schrödinger operator, a self-adjoint version of this, and B was simply minus Laplace. So we have one operator that is simple, and another one that's more complicated, and then we were able to come to results on existence. Yeah, but here these methods are not so suitable, as you will see. And to give a motivation for my approach, I will first of all discuss rank 1 operators, yeah, to give an introduction to what we will actually need. Yeah, so let's note this. Nevertheless, the methods presented so far are not appropriate as they require that the operator B is in some sense simple. Yeah, as we had here in the Cook-Hack theorem. Okay, and to give a motivation for our approach, let's consider rank 1 operators. So, to give a motivation, for our approach, and we consider the case that B minus A, the difference, is of rank 1, is an operator of rank 1 yeah, and this means that the difference B minus A applied to a function phi simply is the scalar product phi psi times some psi for phi in the domain of A and B and for some psi for some fixed psi in the Hilbert space. Yeah, and when you think back to what we had when we talked about Cook's method, yeah, we need the following condition. So let me write it down first of all. In order to apply Cook's method, we seek for for phi in HAC of B. So we seek for phi in HAC of B with the following property, that the scalar product exponential minus ITB phi psi is in L1 of R. Yeah, of R. Yeah. Yeah, why do we need this? When you look back to the assumptions of the Cook theorem, we had there the condition that the integral starting from some lower boundary t0 to infinity of the difference b minus a exponential minus itb phi dt, that this integral was or has to be finite for phi in the space D, which was a subset of the domain of B and HAC of B. And if you apply this to our case where we have this rank 1 operator here, then you see that you have this scalar product term here. So this exponential minus ITB phi now is in the first argument of this of the scalar product here times psi, and then you have a fixed psi, which is not interesting. And then we have the norm of this. So you can pull this, this complex number, this factor in front of the norm so that it stands here. And then you have simply the norm of the remaining vector, which is simply psi, which is a fixed object. So this is not interesting. And then this integral should exist. So this condition, precisely in our case, means that this function is L1. If you transfer the assumption in Cook's theorem to our setting now. So we need phi in HAC of B such that this scalar product is in L1. Okay, let's proceed. Okay, we have that phi is an HAC of B, so since phi is in HAC of B, we know that the measure, D, and here we have the function scalar product E of lambda phi is absolutely continuous. And this means that there is a measurable function, so hence there is a measurable function f on R, so it's a map R to R with the property that the absolute value of f to the power of 2 is in L1. Such that we have that this measure here, d E of lambda phi is simply the absolute value of f of lambda to the power of 2 d lambda. So we can say that this is a density then for what we are doing. And here this simply denotes a Lebesgue measure. So where d lambda is the Lebesgue measure. Okay, and now we can use the spectral theorem in the multiplicator version that we had last week. So let's now apply the spectral theorem. Now, using theorem 4.12, which is the spectral theorem in the multiplicator operator version, where you have multiplication in the Hilbert space with a suitable in a suitable Hilbert space simply with a variable. So for the operator B, we apply this here. Now the fact that, maybe I should recall what we had there. First of all, so that the notation is clear. So this is a reminder here. This spectral theorem says that we have an operator U that starts on the Hilbert space H and maps to an L2 space with a suitable measure, such that the operator, and we apply this theorem here for the operator B, so that b of x is up to this unitary operator u, simply multiplication with the variable lambda for any x in the domain of B. Yeah, so in the suitable L2 space, this self-adjoint object simply is multiplication with the variable lambda. This is what the theorem says. And we apply this now for the operator B. And we had also seen that this map U, this belongs to this reminder block here. This map U was defined from the following relation. Yeah, you can look this up. That's the way how we defined the map U. And then you see that if we apply this for the function 1, then we have that u phi is equal to 1. So using this theorem for B, the fact that u phi is equal to 1, yeah, from this theorem, implies that we get that the scalar product exponential minus ITB phi times psi, this is then the integral over r exponential minus IT lambda, g of lambda, absolute value of f of lambda to the power of 2 d lambda, where the g, so where g is simply u applied to psi, and this is then an object as u maps to this L2 space there in L2 of R with this measure here. Yeah? Yeah, so what did we do here? We know that this expression here is simply u to the power of minus 1. And then we have multiplication with a complex number, exponential minus IT lambda. And then we have u here. Yeah, so this is from the spectral theorem. And we also know that u to the power of minus 1 is u star, as we have a unitary map. Yeah? And then we can throw this to the other side, then it is u. So we get here the function u psi, which I defined as g. And what is remaining is this complex number here, and the u phi is equal to 1. Do you see this? And then we simply get this integral here. This is where it comes from. Yeah, but what do we see from this? Therefore, we see that the scalar product exponential minus ITB phi psi is the Fourier transform simply is the Fourier transform of the function to pi to the power of 1/2 g absolute value of f to the power of 2. Yeah, simply by the definition of the Fourier transform. So we conclude that this expression is a Fourier transform, and we know that this is the function that has to be transformed. Yeah, in general, it is not easy to see when a Fourier transform is in L1. That's not easy. It's not easy to see when a Fourier transform is in L1. Yeah, but what is easy is to get it in L2. Easy is the L2 case. Yeah, so look back to the other blackboard. We want to have that this expression here is in L1, and then we found out that this expression is the Fourier transform of this function here. And in general, it's not so easy to get that a Fourier transform is an L1 object, but the L2 case is easier to handle. So let's keep this in mind for the following considerations. And let's state our next goal here. Let's do it here. We therefore begin by finding a set of functions phi in HAC of B with the property that the scalar product of exponential minus ITB phi psi is in L2. Because this is easier. Okay. Then we need the following definition. This is definition 4.16. Definition 4.16. Let B be a self-adjoint operator with a spectral family E of lambda for lambda in R. Now I introduce a set M, so let script M of B be the set of all phi, in the absolutely continuous subspace with respect to B, for which there is a number R that depends on phi. So I write it as R phi positive. And a function f that is bounded with the property that the support of f is contained in the interval from minus r to r. So it's compactly supported so that we have that the spectral projection at minus r applied to phi is equal to 0. The spectral projection at r applied to phi is equal to phi, and such that the spectral measure corresponding to phi is simply the absolute value of f to the power of 2 d lambda. And d lambda is again the usual Lebesgue measure. So that these three properties here hold, where d lambda is the Lebesgue measure. And furthermore, we define Furthermore, we define the norm of phi, and this is a new norm, so I denote it like this. This is defined simply as the infinity norm of f for any phi in M. Yeah, now what's the interesting thing concerning this definition? Yeah, in general, when we have a function phi in HAC of B, we always have a density such that we have such a representation. This is not surprising. But the interesting thing that we define here, and that is the main criterion for the set M, is that these densities are bounded functions and that they are compactly supported. This is the interesting thing. Yeah, so let's remark this. Remark 4.17. Remark 4.17 for any phi in HAC of B, there is f in L2 such that we have the representation that the spectral measure is simply f of lambda absolute value to the power of 2 d lambda. So this is not surprising. Hence we conclude that M of B is the subspace of HAC of B is the subspace of HAC of B where the densities are bounded and compactly supported. So where the densities F are bounded and compactly supported. Yeah, and now let's note some properties of the space M of B. Therefore, I will have to clean the blackboard. Okay, then let's come to theorem 4.18, which comprises properties of the subspace M of B. So theorem 4.18, which says that M of B is a linear subspace of HAC of B and furthermore M of B is dense in HAC of B with respect to the usual norm on H. So in the H norm. Furthermore, we have that this object that we defined in definition 4.16 is indeed a norm on M of B. Is a norm. Is a norm on M of B. And the proof of this is not very difficult, so I leave it as an exercise for you. It's on one of the next sheets. This is exercise this is exercise 18 then. Okay, but for today we will spend some time on the proof of the next result, which is lemma 4.19, and it says, if we take phi in M of B and psi in H, then we have the following. Then we want to show that the integral over R of the absolute value of exponential minus ITB phi times psi to the power of 2. This can be estimated by 2 pi times the norm of psi to the power of 2 times the norm of phi in this triple norm here to the power of 2. Yeah, and let's have a look at the proof here. So proof. First of all, given phi in this set M of B, there is a number R positive with a property that phi is equal to E of R minus E of minus R phi, simply from the defining properties of the subspace M of B. Yeah, and then, hence, we conclude that the operators bk of phi are also defined. So this object is defined for all k in N. Yeah. Yeah, for example, if you consider this for the case k equal to 1, then you have b phi. And if you consider the quadratic form corresponding to this, then you have b phi phi. This is then an integral over lambda, and you have to multiply with this density f to the power of 2 under the integral sign. And the integral, in fact, reaches from minus r to r because this density has compact support. Yeah, so this object is then defined. And you do the same arguments for higher powers of B. Yeah. And here you use that B commutes with any of its spectral projections, so there's no difficulty to obtain B to the power of k because of the fact that the density has compact support. Then all these integrals will exist, so no problem with this. Yeah, and then we can, when any of this is defined, we can define the following space. So let phi, capital Phi, be the closure of the span of phi, b phi, b to the power of 2 phi, and so on. And you take the closure of this. Furthermore, let's say Q be the projection on phi. So this is the orthogonal projection on this space phi. Yeah, then we can conclude then if we apply this projection to the whole space H, we obtain the range of the Q. This is the space phi. This is an invariant. This is an invariant subspace for B. This is an invariant subspace for B, meaning that QB is extended by BQ. Yeah, why is this the case? If you apply B to some element of the Hilbert space and then you use the projection Q, then you will finally end in the space phi because it projects onto the space phi. This is the projection onto the phi, and if you consider the definition of the space phi, then you find that, as you can see here, it consists of phi b to the power of 2 phi, and so on. And then you take the span of all these objects and you take the closure. So whenever you are in the space, yeah, if you take an element from the space, which is obtained by projecting into this phi, and then you apply the operator b, you will always end in the space, simply by the definition. We have this. And furthermore, if you take the restriction of B to this phi, and of course also to its domain, and this is a self-adjoint operator. So let's take it all together. We consider the range of this projection, which is the space phi, and of course it's obtained by projecting the whole Hilbert space. This is an invariant subspace for B. This means that QB is extended by BQ, as I explained, and furthermore, the restriction of B to this subspace is the self-adjoint operator. Furthermore, in the space phi, simply from the definition, the vector phi is cyclic for B. Restricted to phi in the intersection with the domain of B. This is also clear. Yeah, now we use the fact that phi is in M of B, so as phi is in M of B, there is f in L infinity, the bounded function f with the property that f of lambda is 0 for absolute value of lambda bigger than some r. And we have that d e of lambda phi is nothing but f absolute value of lambda to the power of 2 d lambda. Now, according to theorem 4.12, which is the spectral theorem, so according to theorem 4.12, the multiplication version of the spectral theorem, there's a unitary map. There is a unitary map U that is defined on the range of Q, and that maps to L2 equipped with this measure that is given by the function f, with the properties that we had already seen. U phi is equal to 1, and U applied to exponential minus ITB V is equal to the complex number minus exponential IT lambda U V for any V in QH. Yeah, this is simply the spectral theorem. Now we let the function eta be defined by u q psi, which is then, as the map has the range L2 with this measure here. So this is then in L2 of R with the measure f of lambda to the power of 2d lambda. So that with this abbreviation we get the following. Yeah, we get the following. Let us consider the scalar product exponential minus ITB phi psi. Yeah, this is the object that we are interested in. What can we do here? First of all, I claim that I can rewrite this as exponential minus ITB phi cube psi. So I have added here the projection onto the space capital phi. Why can we do this? Yeah, this object here is nothing but due to the power of -1 exponential minus IT lambda u phi from the spectral theorem. Yeah, but this is then in the space phi. Yeah, because it's the pre-image under the map U. And if you look back to the definition of U, yeah, then U starts on the range of Q, which is the space phi. So this object here lies in phi. And if we take then the scalar product, it's clear that nothing will change when we add the projection onto the space for the other vector. This will not change the scalar product because this is in the space phi. So when we add here the projection onto the space, the scalar product stays the same. Yeah? Okay. Now we use the fact that the map U is unitary. So as U is unitary, we can simply write that this is U exponential minus ITB phi U Q psi. But now we have to pay attention because we are now in the range of the map U, and this is a different space. So this scalar product is now in L2 of R with respect to this measure here. This is important to keep in mind. Yeah. Exactly. Okay. And now we use the spectral theorem here, this multiplication operator version, and then we get that this is the scalar product exponential minus IT lambda u phi multiplied with eta. This was the function eta that I had defined in this L2 space here. Yeah, and we also know that this here is equal to 1. Okay, but then this is nothing but the integral over R exponential minus IT lambda. Here we get eta bar of lambda, the complex conjugate. This is equal to 1, and here we get the absolute value of f to the power of 2 d lambda. Yeah, but we had already seen an object of this type, and we had identified it with a Fourier transform. So this is nothing but 2 pi to the power of 1/2. And here we have the Fourier transform of eta bar, absolute value of f to the power of 2, and the Fourier transform of this object as a function of t. Yeah? This here is simply a Fourier transform. So we can write it like this. Yeah, but now we can apply Plancheret's theorem. So Plancheret's theorem. Plancheret's theorem yields that the integral over R, absolute value of scalar product exponential minus ITB phi psi to the power of 2 dt. So now we integrate the absolute value to the power of 2 of this object here, which is this Fourier transform. Then we see that this is nothing but 2 pi, because we take it here to the power of 2. We get 2 pi, and the norm, the L2 norm of eta bar absolute value of f to the power of 2 and the Fourier transform of this, and this in the L2 norm to the power of 2. Yeah, but now we use this theorem which says that this is the same as 2 pi of times the norm of eta bar absolute value of f to the power of 2 and this to the power of 2. Yeah, but what can we do here? We can estimate this by 2 pi. We can pull it in front of the integral so that we have the infinity norm of f to the power of 2. This is what we can pull in front of the integral. And the rest is the integral over r. And then we have the absolute value of eta of lambda to the power of 2, absolute value of f of lambda to the power of 2 d lambda. Yeah, simply by the definition of this L2 norm. Yeah, and now we can use the fact that this infinity norm there is simply the triple norm of phi by our definition. So now we use that the infinity norm of f is nothing but the triple norm of phi. And we use that the integral that is remaining here, so the integral over r, absolute value of eta of lambda to the power of 2, absolute value of f of lambda to the power of 2, d lambda, what is this? Yeah, this is nothing but the L2 norm to the power of 2 of eta, but now in the L2 space with the measure f to the power of 2 d lambda. And now you have to recall what this eta was. By our definition, this is nothing but the norm of q psi. Yeah. Okay, we had this unitary operator u there, but when we leave this away, we see that this is nothing but the normal L2 norm of q psi to the power of 2. Yeah, because eta was u cube psi, and u is this map that has values in this L2 space here. Yeah, so if we use that this is a unitary map, we obtain the normal L2 norm here of cube psi. And this, of course, can be estimated because this is a projection by the norm of psi to the power of 2. And then we are done. If you look back to the other blackboard, because here we can estimate this integral with the norm of psi to the power of 2, and this is the triple norm of phi to the power of 2. And then you have the factor 2 pi, and this is exactly what the lemma stated. So we are done here. Okay, finally, one final lemma for today. This is now lemma 4.20. Lemma 4.20 for any phi in M of B. We claim that exponential minus ITB phi converges weakly towards 0 when t goes to plus or minus infinity. And furthermore, if C is a compact operator, so if C is compact, then we have that the norm of C exponential minus ITB phi, of course, converges to 0 in norm then. Yeah, so we have strong convergence then here. As t goes to plus or minus infinity. Okay, let's look at the proof. So let the projection Q, the unitary map U, and this L2 function F be as in the proof of lemma 4.19. Yeah, now given psi in the Hilbert space H, we again let eta be defined as U cube psi, which is then in L2 of R with a measure absolute value of f to the power of 2 d lambda. And recall that we had seen that the scalar product of exponential minus ITB phi psi, this was nothing but the square root of 2 pi times the Fourier transform of eta bar absolute value of f to the power of 2 as a function of t. So this is what we recall from the proof of the other lemma. Now, as the function eta is in L2 of R with respect to this measure here, we infer that eta times the absolute value of f is in L2 of R with respect to the usual Lebesgue measure, yeah, simply from this here, and as f is a function in L2, and as f is in L2 of R equipped with a Lebesgue measure, the Cauchy-Schwarz inequality, so the Cauchy-Schwarz inequality implies that eta absolute value of f to the power of 2 is in L1 of R with the Lebesgue measure. Yeah, this is simply Cauchy-Schwarz because if you take the L1 norm of this object, then you can split it into eta times the absolute value of f times the absolute value of f. And here you use that this is L2, and we also have that this is L2. So that is why this works. Yeah, but then can continue here. Yeah, but then we see, hence, our scalar product, exponential minus ITB phi psi, is the Fourier transform of an L1 function. This is now the Fourier transform of an L1 function. Yeah, but then we can use the Riemann-Lebesgue lemma. By the Riemann-Lebesgue lemma, that we had also today, we find that exponential minus ITB phi psi must converge to 0 whenever t goes to plus or minus infinity, and as this psi here was arbitrary, as psi in H is arbitrary, we conclude that we have weak convergence. We conclude that exponential minus ITB phi converges weakly towards 0 for t to plus or minus infinity. And concerning compactness, this is also not very difficult. So, need to use chalk. Finally, let C be compact. Let C be compact and assume for a contradiction and assume for a contradiction that the norm, or let's say that the lim sub for t to plus infinity of the norm C exponential minus ITB phi is positive. Yeah, but then there exists, then there is delta positive, and there is a sequence of t's, a sequence, let's say tk, k element n, such that the tk go to infinity, with the property that the norm of C exponential minus ITKB phi is bigger than this delta for any k in n. Yeah, but we know that C is compact, and we know that exponential minus ITB phi converges weakly towards 0 for t to infinity. Yeah, then you know that compact operators turn weak convergence into strong convergence, so that if we apply the operator C to this, then this converges in the norm to 0, and then this is a contradiction, of course, to this statement here. Yeah, so C is compact and we have this. Then we must have that C exponential minus I TKB phi must converge to 0 when I send k to infinity. And this is, of course, then a contradiction. So we are done here. Okay, this is the point where I would like to stop for today. Next week we will consider another proposition or another lemma that helps us to give a proof of Pearson's theorem, which I will explain in the next lecture. And then we will begin with a proof of Pearson's theorem. And yeah, I don't think that we will be able to handle this before the Christmas break, but we will begin with the proof because it's a long proof. And then we will recall in the new year what we had already done, and then you will understand any detail of the proof, and then we can finally come to this Kato-Rosenblum and Kuroda-Biermann theorem as applications. Okay, I thank you for today, and we see you again next week. Goodbye.